Okay, so let's start with the second half of this of today's lecture. And as I was saying before, K-means is actually considered a machine learning algorithm. It's one of the traditional. It's not deep learning algorithm, but it is considered as a clustering algorithm. Machine learning. Yeah. Let me just set up my view here so that I don't lose viewer. Okay, so let's continue. So K means clustering. Pay attention because we are going to apply this to images, but this could be applied to any sort of data that you have. Well, basically, we're dealing with images as it's just a data set of pixels, right? So most of these of the algorithms that we're seeing, they could be applied to any sort of data sets, and especially K-means has broader applications. So basically, K-means clustering. Each observation will be assigned to a cluster with the nearest mean. An iterative procedure that successively refines the means until convergence is achieved. So basically, the K-means is an iterative procedure that we're going to get the mean. That's what each one of the means for the various clusters, and be updating the mean values of the clusters of points until you get an optimal criteria observed. So let this set of Z1, Z2 to ZQ be a set of vector observation samples. In our case, they are going to be pixels, but they could be any set of observations. Each component of Z1 represents a numerical pixel value in this case, right? In this case, could be the intensity pixel in a grayscale segmentation, or the three vectors in color segmentation. K-means that can be applied for grayscale and color space alike. So the goal then is to partition the set Q of observations into a number of disjoint clusters. Let's call this cluster C1, C2 till CK, satisfying a criterion of optimality, which is this, right? Very simple, very simple. What's this? It's just the Euclidean distance of the mean value of your cluster in your observation. But you're going to get what? You're going to collect the cluster C that minimizes this expression. That minimizes what? Minimizes the sum of distances from each point to each point in a set to a mean of that set, right? So again, it is just if that's the first time that you look at this, that you see, first time you look at this expression, say, oh no, I don't understand anything. What's this? So basically, that's very simple. So that's the Euclidean distance between every observation and the mean values of the clusters assigned, each one of the clusters assigned. I'm going to basically sum each one of the particles, the distance from each one of the particles to each one of the clusters, right? And then I'm going to sum also on the clusters. So basically, I'm going to get this is a minimization criteria. It's a minimization on the distances for every particle to the clusters. So this works like this. There is this visualization here on this side. Let's see. See if I can click on it and let you show that and show to you. That's very important. Can you see that? No, you can't. Collaborate. I'll have to share another application screen. So just hang on a bit. Application screen is now what? Yeah. bigger. So basically, can't start that again. Come on, man. Okay, starting. I can't stop. So this is just a bunch of points, observations, and it's selected initially this 4 clusters in green. So it's calculating the distances of every point to every one of the clusters. Once this is done, it picks up the assigns each one of the particles to the clusters that are closer, that are nearby, and they start again this procedure, trying to optimize that minimality criteria until they find the clusters that are at the minimum distance to each one of the particles. Okay, let's see again. I think that's a good. We should see again to convince ourselves that what's doing is correct. So it calculates the distances for every particle to each one of the centers. It updates the center, calculates again, updates the center, calculates again, until the clusters are not changing anymore. Right? That's the basic idea. Let's go back to the slides. Okay, so right. Okay, so we're back at the slides. So that's in a nutshell. That's what k-mean does. But let's see a little bit in details the various steps of this algorithm. So there is the initialization procedure. You have to specify an initial set of means. This is usually randomly picked, just randomly picked. There's one thing that you should be aware of when you're running k-means is that you should give the number of clusters. They don't find it doesn't optimize the number of clusters. If you're given 4 clusters, it will get the 4 optimal clusters. But if you give me the best number of clusters, it doesn't work that way, right? There's you need another algorithm to choose the clusters. But let's try to understand the k-mean. So you're given a number of clusters and picked up randomly centers for your means values. Then you're going to assign samples to clusters. That's the stuff that you've seen in the demonstration. So it's basically calculating the distances from every particle to every single cluster center. So basically assign each sample to the cluster set whose mean is the closest. So basically it's going to assign a sample to a cluster means that we're going to label each one of these pixels into one of the classes that I want to use. Classes is not a very good name. You can use classes for k-means, but in terms of segmentation, into the region. So you can see these classes of k-means as regions, distinct regions to which we want to segment. So and then you update the cluster centers. How do you update that? Just take the mean value. The mean value with respect to the number of samples in the cluster set. So, and then you test for completion. You basically see if the clusters haven't moved enough. So a lot, right? So just to get, I'll have to get back again. Just to understand this bit here, so once you calculated the distances from each particle to each one of the other particles, you get the mean value of all of these particles that you assign to the nearest clusters as the center of the new center of the cluster. That's the part that you've seen in the example that the clusters were moving from one point to the other. They were moving to the average value of all of the particles that have been assigned to them. And all of and a particle had been assigned to a particular cluster if the distance between the particle and the center of the cluster was small, was the minimum of all the distances calculated. Is that clear? Maybe I explained it in so many ways that a very easy thing became a very complex thing. And I think K-means is so important, so important, so important that I urge you to read the section on the book about it. It's on page further down. Been talking too much. Yes, it's page 10.5, page section 10.5, page 770. Okay, good. Let's move on. So that's then the result of using k-means for segmentation. K-means clustering for segmentation. If you want to segment the old cover of this book, you have a very nice, easy segmentation. What's the caveat of that? Had to give the number of k, the number of clusters. So basically, it's being segmented into one, two. One cluster was white, another cluster was black, and another cluster was gray. If I had given 2 clusters, it would have segmented in a wrong way. If I have given 4 clusters, maybe I would have more distinctions here. That all depends on the kind of points that you have on your observation set. Another good method, this is quite a recent method, it dates back from 2010, I believe. That's the region segmentation using superpixels. Right. So if you understood how k-means work, you're going to understand superpixel segmentation, because basically what superpixel is the application of k-means on small regions. So it's more or less like, in a nutshell, what k-means, in order to segment this image, you apply the clusters, and all points of the image were possible to be assigned to every single cluster. So I had to, it was a quite heavy procedure, right? Where I had to assign every point in my observation set to every single cluster, which one had the shortest distance. With the superpixels, then I applied a kind of k-means, but on now another grid of the image. So I'll create a grid of many regions in this image, and then I'll apply a little k-means in each one of them. There's a question here. Let me see. Right. Ziwen asked a very good question. How should we know how many clusters should we set? Right. Yeah. If you know, that's all previous knowledge that you have to have. So if you're segmenting into regions, if you want to segment your image, you know on what you are segmenting. So what is your criteria for segmenting? So for instance, I want to segment the regions that are red, the regions that are gray, and the regions that are yellow. So how many clusters do you need? 3 clusters, right? You don't know how to segment this image. The algorithm is going to find the best segmentation for it, but you know on what you want to segment, right? So if you're looking at a very texturized image, such as this one is not. Yeah, it's not as if you get the cygnus loop image that we've seen in the first part. This one. So you don't know this region, right? So we want to segment out this region. So that I need to apply some measurements or whatever I need to apply for this region. But you know that this will have one kind of texture, another kind of texture, and another kind of textures. Again, how many clusters? 3 clusters. That all depends on your goal. And the problem is is that it's very well applied if you know the problem. It's not applicable for instance, machine vision. For machine vision, unless you're for broad machine vision, right? So we're to a robot is going to walk around our department serving tea for everybody around, right? And you want to use segmentation. K means to segment the people around. It's not used for that, right? So it depends on. You have to understand how to apply each one of these of tools, each tool that you have. So K-means not applied on a broader sense. It's applied if you actually know what you want to extract from the image. All right, thanks for the question, and keep them coming. So we're talking about superpixels. Basically, the main idea is that I want to replace the standard pixel grid. So what's the standard pixel grid? It's just a matrix of pixels, right? It's no grid. It's just each pixel separately. That's where K-means is working. So I'll replace that by groups of pixels. I'll select a number of primitive regions that have some sort of perceptually meaningful, if you know what perceptually meaningful is. But if you don't know, you just get a grid of pixel regions. This will obviously lessen the computational load because you don't have to calculate the centers for your clusters for every single pixel in your image. You just need to calculate the clusters for each one of these regions. It improves the performance of segmentation algorithms in this way, right? So it actually reduces irrelevant details and irrelevant computations. So in a nutshell, K-means that's superpixel segmentation is K-means applied to each neighborhood rather than in the entire image. So that's basically what you get from K-means. So this has been set up as very tiny neighborhoods, very tiny grid, and it's segmented each one of them in terms of, it's kind of modified each one of these regions. So each one of these regions is a superpixel segmented, right? So that's quite, that may be too detailed, but the main application of superpixels are when you actually need detailed things. So if you're doing robotic surgery, for instance, if you are doing image analysis for medicine, you don't need to miss stuff. So you need a proper segmentation, very big, tiny segmentation. But you can change the sizes of these regions, right? So you get a kind of a not so precise segmentation, but still a good segmentation. So these are the results of using 1,000 superpixels. This is the result, and that's we get this kind of segmentation. Right? There's 1,000 superpixels and 500 superpixels, and then 250 superpixels. So we get this kind of segmentation here. So we're gonna see in a simulation how the superpixels work, so that you're gonna have an idea. But let's understand the algorithm first. Its algorithm is it's called simple linear iterative clustering. That's SLIC. This is a very famous algorithm. So SLIC observation typically use 5D vectors. Basically, it's going to run on your RGB image. So you have an R value, G value, B value. These are intensities in the R space, in the intensity of the pixel in the R channel, in the G channel, and in the B channel, and the spatial position of the pixel, right? The XY position of the pixel in the image. So, and I have to set up, these are the parameters of SLIC. There's always some parameters to set. NSP will be the desired number of superpixels. and the total number of superpixels, the total number of pixels. So the desired number of superpixels is going to be how precise will be your grid, how precise is going to be your grid that you set up as a parameter. The number of pixels is the total number of pixels, right? So it doesn't change. And we're going to set up the initial superpixel centers, which we're going to call MK, and the centers will also have a value RK, GK, BK, and XK and YK. And these are obtained by sampling the image on regular grid spaces S unit apart. What's S? S is basically the average of the total number of pixels that you have over the number of pixels that you want. So basically, you divide the image with the given. If you have a thousand, if you want to have 1,000 superpixels in your image, you're going to divide it into 1,000 pieces, right? There's some minor issues. I'm not going to get into detail. Let's just see the big pictures. So the distances are computed according to each center. So you're going to have what? A distance in the RGB space, which basically your value in the cluster center. This is going to be calculated for each cluster center, right? The value of the cluster center to each one of the pixels around that region. And this is for the red channel, the green channel, and the blue channel. Basically, this is a measure of distance, Euclidean distance in the color space. This is saying how distant the pixel I is in terms of color to the distance of the center of this of your superpixel, and also the distance between the spatial distance. So there's a distance in the color space, Euclidean distance in the color in terms of color, and the Euclidean distance in terms of in the spatial place. So the similarity. So one pixel will be similar to your cluster center by just a measure of the distance in the RGB space and the distance in the spatial domain. Right? So let's see an example. This was a very good example. It's actually an excellent 7-minute video on YouTube. I recommend you to watch it and follow that guy. The guy is excellent. He explains very well. The 7-minute explanation of the superpixel segmentation. So basically, if you want to calculate the distance from this pixel P1 to this pixel P2, and then the distance from this pixel P1 to this pixel P3, you have n, that's the total number of pixels, right? So 1, 2, 3, 4, 4 by 4. And K is how many regions I want to segment, right? How many superpixels I want to get. So you're going to have this value S is going to be 2. And then this value M is, what's M is the, gosh, I forgot what M is. M. Yeah, I have to get back to you. I've just seen this example, and then I'm missing that bit. But basically, it's a calculation of this distance, right? This is a weight you put on the distance dxy and dRGB. I'll get back to you about the M. And then basically, this is the distance from pixel P1 to the pixel P2. There's a value. And there's this value of the distance from P1 to P3. And given that, so that's the main calculation that it does on the on applying this k-means. So not a simple distance, is a distance based on all of these criteria that I just explained. So that's the basic SLIC algorithm. So you initialize algorithm, compute the initial superpixel cluster centers. by sampling the image at regular grid steps, as explained. Then that's just a technicality. You're going to move the cluster centers to the lowest gradient position in a 3x3 neighborhood. Then you're going to assign samples to cluster centers, similar to what K-means does. For each cluster center Mi, compute the distance Di between M and each pixel P in a 2S by 2S neighborhood. So S is the size of your neighborhood, right? About the center. Then for each point in this neighborhood, you're going to calculate whether this distance is less than a certain specified distance there. I want it to be within that particular cell in this supercluster. And then we're going to update the cluster centers by picking up the mean. Again, that's k-means, right? And test the convergence. I'm going to stop converging this cluster movement once the movement becomes very small. In post-processing the superpixel region, we're going to replace all superpixels in each region by their average value. So that's the main reason for so you're segmenting by taking similar pixels in the superpixel region that's been modified by this kind of localized k-means and use this and assign it the average value of the superpixel of the center of the region, right? So basically the centers will move around the grid space in order to find a better position in terms of the distances. Cluster centers will be the superpixels. And I think we could check, it's good, we still have time. Let's check this animation here, which is quite interesting. Just a minute, because there is YouTube propaganda. Yeah, here it is. Okay, so I'm gonna have to replace. Lost you. Okay. Let me stop sharing this, and I'll start sharing another application. Okay. So basically, the cluster centers are moving, as you see, by using k-means. And then at the end, when they stop moving, they just assign. It's not an actual application of the SLIC, but it's a very closer application. So you're moving basically the shapes of these regions and assigning the value of the center to the entire region. And I recommend it's just 7 minutes to watch. Very nice explanation of the SLIC method. And I'll stop sharing this, and I'll start sharing the other thing. Okay. So, so this is one example of superpixel. So this is what we obtained with Otsu. Remember that, the segmentation of these iceberg. By using superpixel segmentation, and I get a much better depending on what you want, what you mean by better, right? A more precise segmentation. So I have a more distinctive. So this region here, let me get this pointer. Sorry. No, not the pen. So this region here that has a variation of intensity, I could segment it quite well. Whereas this background here, which has more or less the same by superpixel segmentation. These were still segmented by distinct regions. But once I assign a label to these regions, as this background was pretty much homogeneous, I just get one single homogeneous region here, all with the same value. Right? That's the beauty of it. And if I want more precise, so you see like this portion here, this kind of a slope, shiny slope. It's well represented by this region here, whereas the white part here, which has more or less the same values, they all received the same value. Although they were segmented, if you look closely, they were segmented by distinct regions. Same thing as the background. They were segmented by distinct superpixels, but once you assign the value of the center to the value of the entire region, that's one label. So what you want to label. So if this label is exactly the one that of the other label, you have one large region, right? And okay, I think I'm over with superpixels. It's another key algorithm. And I've seen it used a number of times. That's a very powerful algorithm. It's older than superpixel, but for some reason, which I don't know why, it has from the region segmentation algorithms that we've seen today, graph cuts is the most famous and the most powerful. I think just because it generates a representation of the image as a side effect of the algorithm. And but before we start with graph cuts, I need to ask you a question, and you can answer it by the using the chat. Do you guys have a course or have some knowledge of data structures, such as graphs, trees? Okay, you do, But you, Zuen, you are in the engineering department or computer science? CS, yes. So CS has to know that. Well, Lachlan, you are from engineering. Do you have this stuff of data structures on engineering? Well, because basically, in order to understand it, the graph cut, it goes not too deep. Okay, so you've seen some before, right? So basically, to everybody else now that may watch this lecture later, we won't survive on this field if you don't have a good grasp of data structures. So try to find some. If you don't know, if you don't have this as background knowledge, try to get some book about data structures. This is one of the key aspects of all of the methods that we're going to see from now on, right? And if you're going to continue in this area, you should understand that. So graph cuts is another key method. Basically, well, the idea is to separate foreground and background, and it works better than other algorithms for very complex images, for natural images, right? So if natural images have a very complex background, and what is a complex background? That is not homogeneous, right? So whatever side if you're not looking straight into a white wall, if you're looking at something else, the background is always going to be full of objects. So that's a complex image for you. It's very difficult to segment. The idea is then to partition the images into regions expressing the pixels as nodes in a graph, right? So once you have every pixel will be assigned to a node in a graph. Then we're going to have to find the optimal partition. That's called the optimum cut into groups of nodes. The optimality criteria will be, well, I want to keep pixels that are similar in the same group. And groups of pixels that are dissimilar to other groups, I would like to cut. So basically, the optimality should assign high values for a member within a group, or basically an homogeneous region, and low values for members across groups, for distinct groups. Right? So this will be used undirected graphs, basically a bunch of vertices and a bunch of edges with them without directions. The edges will be characterized by a matrix W, W representing the weight of the edge connecting vertex I from vertex J. So let's stop here a second. So each vertex of a graph will be assigned to a pixel. And the pixels are going to be connected together by an edge by a weight, right? They're going to, every pixel that's next to the other is going to be connected by an edge. And then each edge will be assigned a weight. And the weight will be dependent on how similar the pixel is. And similarity criteria, as I explained before, you choose. Could be color, could be texture, could be whatever you want, right? So that's basically understood. So this is written here. So weights are proportional to the similarity between pairs of adjacent nodes. So basic idea then is to have the image segmented as weighted undirected graphs. Nodes will be assigned to pixels. An edge is defined between every pair of adjacent nodes. Then will be defined using spatial relationships, distance or intensity values. The weight of the edge will be defined using spatial relationships of intensity measures. Would be a measure of similarity between nodes. And the idea is to partition the nodes of graph into disjoint subsets where similar nodes, the similarity between nodes within a subset will be high, meaning the weight between the edges in the pixels in the same set will be quite high. And the similarity across nodes of distinct subsets will be low. And when it's low, I segment it and cut the connection, the edge between two vertices. So now that we understood in an abstract way, let's see an example. So imagine that these are all pixels. So I have a 3x3 matrix of pixels. Each pixel has an intensity value, and each one of these intensity values are different from one another, right? So this is black, this is white, this is dark gray, this is white gray, and so on and so forth. So every one of these pixels will be assigned a node in a graph. And pixels that are adjacent to one another, so for instance, this pixel is adjacent to that, will be connected by an edge. So pixels will be nodes. Adjacency between pixels will be defined as edge in the graph. And if you apply a similarity criteria here, that is how similar, the similarity criteria based on the pixels on the pixel intensity. So this pixel, the intensity of this pixel is pretty similar to that. And this one is not so similar to that, right? So this is dark gray, it's almost as black as this one. So this would be very similar. And well, as these are very similar, so you have the thickness. The weight is represented as thickness of the edge will be, so this will be thicker, right? This edge connecting this pixel to that, the other pixel will be thick, the edge will be thicker than the edge connecting this to that. So the distance from this intensity to that intensity is larger. So that will be a very thin edge. So the same thing for every pair of adjacent pixels. Where am I going to cut? Where am I going to segment the image? Very easy. You just cut it through the lowest links. All right, the lowest links are always the trouble, so you cut them off. So basically, how then I segment it? This will be one region in a segmented image. Just paint it with one value. This will be this one region. And these other pixels will represent other region, and not as a distinct image in the image. You just paint it in white, for instance. That will be the other region. Is that clear? Okay, so just to make it clearer, the degree of similarity between pixels or nodes will be inversely proportional to the difference in their intensities. The closer the intensities between adjacent pixels, the greater the similarity value. It could be defined as a degree of similarity could be defined as a function of the gradient as well. Basically, you can define whatever degree of similarity you want. So it's a very versatile method. Anything, basically, as I said, anything that's pixel quality, you can find as a similarity between pixels. And the similarity is illustrated as thickness. The more similar, the thicker is the edge, the thickness of the edges, right? More similar, thicker the edges. And for segmentation, you just basically cut the weakest links. Okay, so that's the main idea. So the actual algorithm, it works with two other concepts. It's not only it's based on this on what we explained here, on this connectivity of pixels connected to graphs, but it also based on having two other nodes in these graphs. They are basically what we call source or sink. So source terminal node, source node will be represented as background, and the sink node will be representing foreground pixels, and they are all related. So if these are defined as foreground pixels, given the similarity criteria that we defined before, the edges connecting the source terminal to background pixels will be stronger. We'll have a larger way, so we have will be thicker edges, and the edges the same thing with the sink terminal representing foreground. So why do we do that? That's basically in order to color it properly, to segment it properly. So now I want to segment it into foreground and background nodes. So basically connecting the foreground to foreground nodes to a node representing foreground and background nodes to a node representing background. These are called T-links. So T-links are links that connected nodes of the graph to the source and sink terminals. And they are used to associate each pixel to a probability that it is background or foreground pixel. The probabilities are represented as the weights of these T-links. Right. So how do you set this probability? That is a very good question. That is a very good question. The simple answer is that it's not easy, right? Automatically, it's very difficult. Automatically, you should have some measurement of pixels in a neighborhood. But this method is basically largely applied in one particular area that uses image segmentation. That's image segmentation by iteration. That's iteration with an N. No, it's not iteration. The user interact with the image. So, for instance, how we are going to set source and sync on this image using this interaction procedure. The user may well scribble on top of the image, saying, "Well, this is then foreground, and this is background." And the user doesn't. But this is a very raw image. But if you have a more complex image, let's get a more complex image here. Here. So in this method, the user could just say, Well, this is roughly one region, this is another region, and this is another region. This input will be used to calculate these probabilities of source and sink, and will give you a quite good segmentation. There's a whole area of research of developing this kind of methods, these graph cut methods. And the choice always depends on the system's design, on what you want to do with the system. Let's see a little bit closer to finish this lecture. What does it mean exactly, this optimum partition of graph? So basically, you have to assign a weight to each edge. The weight is assigned to pixel by pixel, to adjacent pixel, and also to every pixel to a source sink terminal. And you have to cut through weak edges. The best cut will be the minimal cut, that one that minimizes the global energy of the graph. So basically what you're going to do, you have to find a cut whose sum of edges, some of edges in the cut, some of edges that you are cutting, some of the, not the weight of the edges that you are cutting, that's minimal. So basically you want to minimize this, this expression here. So we could use a formula to actually define on which edge is more similar to the other. So this is just a kind of it's a Gaussian distance here, right? So there's 1 divided by the distances between the pixels I and j, and this is the exponential of this kind of value here. But the important thing is that this is the intensities of pixel I, and this is the intensity of pixel j, right? You can set the weight. If you set the weight on this way, basically, if I has more or less the same value, if the intensity of pixel I has more or less the same value of the pixel j, then this will be 0, and this exponential will be 1. If they are distant, they're different, then this thing here will be minus a big number, will be a negative big number, right? Which will be closer to 0. Basically, this connection between pixel I and j, if this happens, if this is measured, can be severed. Whereas if this happens, then I won't cut through the edges. So what's the problem? There's always a problem with these methods. If you think them in very basic terms, is that there's an exponential number of partitions, right? It leads to an intractable computational problem. We're going to solve that. And so just to finish, then there is one simple solution, and that would be the introduction for our very long lectures that's on chapter 11, feature detection. So one of the solutions that's described on the on our book is the it's a Ch and Malik solution. And Ch and Malik solution uses one thing that's that we just mentioned in this topic, but we've never seen it applied, which is the linear algebra. Let's open a parenthesis on basic definition of linear algebra. You probably remember from the very early your very early topics in whichever STEM course that you did before. So let's recall the definition of eigenvalues and eigenvectors. This is taken from the review material that's on our book's website. So basically, the eigenvalues of a real matrix Rm are the real numbers lambda for which there is a non-zero vector E, such that this non-zero vector E multiplied by matrix M is equal to this eigenvalue lambda multiplied by the same vector. So what's happening here? So why do we use this? A matrix can be a big thing, right? A matrix can be a big and complex thing. But if we find if you find a value lambda in a smaller, a simplified vector, this guy here is representing the same thing as this very complex thing. So that's wonderful, right? So we can do all the computations with these eigenvalues and eigenvectors. And more than that, the eigenvalues and eigenvectors, they are actually representing some essential characteristics of your matrix. And we are going to use these characteristics here to solve this problem, to solve the graph cut problem, how to partition a graph cut. But in the next lectures, this is essential to understand some feature detection, some very modern, very important feature detection algorithms. So, okay, so just an example. So consider a matrix, this matrix here, that's 1, 0, 0, 2. You can verify yourself that, this matrix has 2 eigenvalues and 2 eigenvectors. So this matrix is clearly represented by lambda 1 times this eigenvector. Here is just 1, 0. You just multiply, lambda 1 is 1, right? So you just multiply lambda 1 by E1, and then you're going to get the same result as multiplying M by E1. And you have another eigenvalue, another eigenvector, another eigenvalue representing the same matrix, which is this lambda 2 equal to 2, and E2, the eigenvector E2, that's 0, 1. You can make this, multiply M by E2, and then multiply lambda 2 by E2. You get that this is the same value. So in other words, E1 is an eigenvector of M associated to the eigenvalue lambda 1, and E2 is an eigenvector of M associated to the eigenvalue lambda 2. But you can see that, so you see this value here is smaller than this value 2. So what does it mean? We'll see what it means in a minute. Oh gosh, it's almost 5 o'clock. So by that, we are about to finish. So Shia-Malik solution. Basically, what they did was to approximate the discrete solution for this minimization procedure here in terms of generalized eigenvalue problem. So where D is the diagonal matrix with the main diagonal representing the k nodes of a graph. So D is representing the graph. W will be the weight matrix. W is representing the weight of the edges connecting the nodes of this graph. So this always gives k eigenvalues and k eigenvectors, right? So there's always a matrix has a number of eigenvalues. Any matrix has a number of eigenvalues and eigenvectors. So basically, there's lambda d will be the eigenvalue. What the minimization problem then would be solving this equation, right? Solving this equation. So basically, the solution is very simple. Once you get it, it's just applying this notion. In order to reach the solution, I don't know what the guy took to have this idea, but so basically the idea is to find the eigenvector with the second smallest eigenvalue. And you're done. That's where you're gonna cut your graph. And this is based on linear algebra, and I've been a few years that I want to get back at my linear algebra and de-rust it, actually to go deep into linear algebra, because this is fantastic. So what it means to get the second smallest eigenvalue. The second smallest eigenvalue is the minimal, right? So that's the Fiedler eigenvalue, which defines the algebraic connectivity of a graph. So actually, it's representing the connectivity. The second smiler's eigenvalue is defining the connectivity of the graph. The first eigenvalues represent the connected components of the graph, and the second represents the clustering of nodes. There's a whole bunch of explanation about this on this link. And that's basically what the solution of Ch10 is. And why it works? Basically, you have to solve this equation. How it works? You have to solve this set of equations and choose that the smallest value is that has the second smallest eigenvalue, and that's basically it for the graph cut algorithm, right? So the algorithm is described on page 785. Please read this algorithm, and that's basically what I said here. But just for you to get a little bit further on understanding the various steps. Okay. Do you have any more questions? If not, I'll close this lecture and I'll see you next week. Thank you for coming. And next week we start with chapter 11. There's just one bit that I will definitely skip because that will be too much. Which will be the section 10.7, that segmentation using morphological watersheds. Not because it's not important, but because I think it would be too much. Let's see something different. Enough of segmentation procedures. Next week we go to feature detections, which is a very interesting subject. Okay, I'll see you next time. Bye.